So today we're going to be talking about nodal analysis. And as I have mentioned previously, it is a very powerful tool that can be used to analyze practically any circuit. It is best used for complex circuits and all that kind of stuff. We'll talk about what that means in a little bit here. But we are going to learn the process of nodal analysis by working example problems. So I like to teach nodal analysis as kind of an algorithm or a step-by-step process. And if you follow this process in this particular order, I cannot emphasize that enough, you will come out with the correct answer every time. If you want to play fast and loose with my order of doing things, that's perfectly fine by me. Just know that when you ask me for help because you've made a mistake, I'm going to have you redo everything in exactly the order that I'm about to tell you to do it, because it's the best way to do it. All right, so the circuit that we are going to analyze is this guy here. So we've got a big wire, a 15 ohm resistor, across which we are going to define some voltage Vx. Here we have a 5 ohm resistor, a 20 ohm resistor. Down this leg of the circuit, we have a 10 ohm resistor. We're going to have a 2 amp source here. And then we're going to have a dependent source here. 0.5 Vx. I want you guys to please notice that at this point in time, there are no voltage sources in our circuit. So we're going to learn nodal analysis with current sources only. And then after we get a grasp of how it works, then we're going to introduce voltage sources, because that tends to mess things up a little bit. All right, so our first step is going to be simply identify all of our nodes. So I'm going to do this like I've done every other time in this class. I'm going to use different colors and just go from one component to the next, like so. So I have this red node at the top left. I have a green node here at the top right. I have a blue node here in the middle. And I'm going to put a pink node on bottom. So that's all step one entails, is literally just identifying your nodes. Okay. Step number two we will need to select a reference node, and this is commonly called ground. So really what we're doing is we are saying one node, and we get to pick whichever one it is, has a voltage of 0 volts, and then we're going to measure everything else with respect to that reference of 0 volts. Okay. So generally speaking, the best choice for our reference node in a circuit like this that only contains current sources and then resistors and stuff like that, is to choose the node that is connected to the most amount of elements. I like this circuit because every node is connected to exactly 3 elements, so there is not an obvious choice. So we can pick literally any node, and the results are going to come out the same. So Abram, tell me which node is going to be our reference node. It is completely arbitrary. The pink one. All right, the bottom. That is a pretty common choice. Like I said, there are no wrong choices. And in this particular case, there are no particularly good choices either. So the bottom node is as good as anything else. All right. So we denote our reference node by using this ground symbol here. Okay. So all this means is that the voltage at this node is exactly 0 volts. And it's going to serve as a reference for every other voltage that we find in this circuit. All right, so step number 3, this is our last setup step, is going to be assign nodal voltages to all non-reference nodes. So I'm literally going to go to my other 3 nodes and I'm just going to say they have some voltage, and I'll explain what that voltage means here in a moment. So if I were to call my red node node A, then I would call this nodal voltage VA associated at this particular node. I can call my blue node, it will have a nodal voltage VB, and my green node will have a nodal voltage VC. So what I'm saying is that the voltage at node A with respect to ground is voltage VA, the voltage at node B with respect to ground is VB, and the voltage at node C with respect to ground is VC. So VA is literally the exact same thing as this voltage drop across the 10 ohm resistor, where the positive polarity terminal is at node A and the negative polarity terminal is at ground. That's what a nodal voltage means. Wherever we put the designation, that's the positive polarity terminal. Ground is always the negative polarity terminal of a nodal voltage. Okay. So similarly, we could say that the voltage drop across the 2 amp current source is the same thing as nodal voltage VB, and the voltage drop across our dependent current source is the same thing as nodal voltage VC. I'm just trying to show you how these nodal voltages relate to how we've been expressing voltages up to this point in this class. This is getting busy, so I'm going to erase these extra representations here in just a moment. So anybody have any questions about what a nodal voltage means? Yes. So the positive polarity terminal is whatever node I want, and the negative polarity terminal is always ground. Always, always, always ground. Okay. All right. So now we are into our analysis. So step number 4. We are going to perform Kirchhoff's current law at each non-reference node. So I will have a KCL equation at node A. Then I'll write another KCL equation at node B. And then finally a KCL equation at node C. And I will come up with a system of 3 equations and 3 unknowns. Actually, sorry, I'm not feeling well and I've made a mistake here. This shouldn't be step 4. This will actually wind up being step 5. So I'm going to be lazy and move this down. I missed something. My apologies. So I just missed one of the very easy to miss steps. So again, I apologize for that. Let's fix this. Step number 4 should actually be to express any controlling variables in terms of our nodal voltages. So the reason why I put this before we actually do our analysis is because it's so easy to overlook. So usually when you're using nodal analysis, and you'll see with mesh analysis on Friday, you get so used to writing your KVL equations and KCL equations that you sometime overlook where the other equations are going to come from, which I literally just did, okay? So I like to ask you guys to write your extra equations first because they're so easy to overlook. And it gets you in the habit of doing them first so that you'll always wind up with the correct number of equations and all that kind of good stuff. Okay. All right, so for this particular circuit, we only have one dependent source, so we only have one controlling variable. Our controlling variable is this voltage Vx. So this voltage Vx is controlling our dependent source. So we need to figure out how to express that voltage Vx in terms of our nodal voltages. For a voltage, it's particularly easy, okay? So we can express any voltage in a circuit when we're using nodal analysis simply by saying whatever nodal voltage we have at the positive polarity terminal. So what nodal voltage is at the positive polarity terminal of Vx? Vc minus whatever nodal voltage is at the negative polarity terminal of Vx, which is Va. Absolutely right. So our controlling variable Vx is defined to be the potential difference between node C and node A, which is exactly what the terminals tell us. Okay. So now we can get down to performing Kirchhoff's current law. So I'm going to write KCL equations such that the current will be leaving my node of interest. So when I'm writing my KCL equation at node A, all I'm doing is really adding these three currents together. They're all leaving node A, and then I'm setting them equal to 0. Okay, so that's nothing more than Kirchhoff's current law. And I'm choosing to do it where all of the currents that are leaving are positive, so that everywhere I have a VA term, it's going to be positive. So whatever node I'm performing KCL at gets positive signs, and all of the other nodes are going to wind up having negative signs. It's a nice, easy way to organize things without having negative signs all over the place. So we are going to just use Ohm's law effectively in order to express all of these currents. So let's start with the current flowing down through the 10 ohm resistor, okay? So that would be the voltage VA minus 0 divided by 10 ohms, okay? So the VA minus 0 literally just represents the voltage drop across the 10 ohm resistor. And then we're dividing it by the value of the resistance because that's how Ohm's law gives us current, okay? So if you ever are in doubt about which node should come first, effectively you're writing the equation such that the node that the current is leaving from minus the node the current is flowing to divided by the resistance, right? So this current right here is flowing from node A to ground. So that's why we have VA minus 0. And then we divide by the resistor value. So let's do the same kind of thing, but now let's look at the current flowing from left to right through the 5 ohm resistor. Who would like to attempt to tell me what this expression should look like? Janae. VA minus VB over 5 ohms is absolutely correct. All right, now we have the current flowing up through our 15 ohm resistor. Who wants to tell me what that's going to look like? Brennan. Absolutely right. VA minus VC over 15 ohms. So in literally every case here, all we're doing is we're saying a current starts at VA, so that's why it's the first thing in all of our expressions, minus whatever node it flows to, divide by the resistor value, okay? Nothing hard or magical about this. It's literally just Ohm's law. So now let's do KCL at node B. So at node B, I'm going to have this current flowing to the left, this current flowing down, and this current flowing to the right. We're going to add those three guys together, set them equal to 0. Brandon, could you please tell me what the current flowing to the left through the 5 ohm resistor is? VB minus what? Yeah, VB minus VA over 5 ohms. Absolutely correct. Patrick, tell me what current I have flowing down through the current source, please. -2 amps. So the direction that we're trying to find the current in is opposite the direction that the current source is pushing current, so we use a negative sign. Absolutely correct. Let's see. Liam, tell me what current is flowing right through the 20 ohm resistor. Absolutely correct. All right, so we had 3 currents. We have 3 terms. Set them equal to 0. Move along to our next node. So now we have KCL at node C. So at node C, I'm going to have this current flowing to the left, this current flowing down, this current flowing up. Mallory, please tell me what current is flowing to the left through the 20 ohm resistor. Absolutely correct. VC minus VB over 20 ohms. Molly, could you tell me what current I have flowing down through my dependent current source, please, ma'am? So whenever we have a current source, it's just the current supplied by the source. And if the arrow of the current source is in the same direction as our arrow, we don't make any changes. If it's in the opposite direction, we put a negative sign. So take another crack at it, please, ma'am. 0.5 VX, that's it. Absolutely, thank you. And then lastly, we have our current flowing up. And then through the 15 ohm resistor from right to left. John, you want to help me out with that one? So the current flowing up, leaving node C. We're not looking at VX literally at all. What node does the current start from? It starts from VC. So we're going to have VC. What node does the current flow to? All right, so VC minus VA. What's the resistor value? So divided by 15 ohms. VX literally doesn't matter at all when we're writing our KCL equation. The only place that it, I guess, kind of matters is here, and that's because there's a current source telling us very explicitly that there's some fraction of Vx that's flowing down there. But for all of our resistor relationships, it's just what node does the current start from minus what node the current flows to divided by the resistor value. Nothing else matters. All right, set this equal to 0. So how many unknown quantities, Elizabeth? So that was literally going to be our next step. So how many unknown quantities do I have? 4, right? VA, VB, and VC, my 3 nodal voltages, as well as Vx, my controlling variable. How many equations do I have? I count 4. Right. Here's my first equation, 1. My second equation, 2. Third equation, 3. Fourth equation, 4. So if you happen to take my advice and buy a Casio 991 calculator, you're good to go. Because a Casio 991 can solve a system of 4 equations and 4 unknowns. If you did not happen to buy that particular calculator, let's say that you bought a Casio 115 or a TI-36X, now we need to make a substitution to get rid of one equation. And as Elizabeth suggested, we can simply substitute in this relationship, Vx is equal to Vc minus Va in right here. And now we have a 3 equation, 3 unknown system that we can solve with any of our non-peasant calculators. So we could simply substitute in Vc minus Va, call it a day. So we have now a 3 equation, 3 unknown system, which can be solved with any of our calculators. So let's solve it using our calculators. If you have any questions about how to solve the system using your calculator, please let me know. Ashton, can I borrow your calculator? I've got at least 2 of this exact calculator that are more beat up than this. That's good enough. So, I am going to talk you guys through what I'm inputting into my calculator, or Ashton's calculator as the case may be. So I'm solving for a 3 equation, 3 unknown system. And so for my coefficients, or my variables are going to be VA, VB, and VC. And so the coefficient for my VA term is going to be 1/10 plus 1/5 plus 1/15. And I'm going to put it in the calculator literally like that. I'm going to let the calculator do all the math for me because I'm incredibly lazy and I don't want to screw up finding the least common multiple or whatever the hell it is that you do to make fractions look pretty. That's what calculators are for, right? So I'm literally putting in 1/10 plus 1/5 plus 1/15. Before I move on from here, does everybody understand where those coefficients are coming from? So VA is being multiplied by a factor of 1/10 because of this guy, 1/5 because of this guy, and 1/15 because of this guy, right? My coefficient for VB from my first equation is just going to be negative 1/5. My coefficient for VC is negative 1/15. And then I need to move my constant term, if I have any, over to the right-hand side of the equal sign. For this equation, there is no constant term, so I'm just going to leave that as 0. For my second equation, my coefficient for VA is going to be what, Joy? Negative 1/5. Absolutely right. Thank you. What's the coefficient for my VB term going to be, Hannah? 1/5 plus what? Yeah, 1/5 plus 1/20. Thank you, ma'am. It's getting old, can't hear. My coefficient for my VC term, Austin. Negative 1/20th. All right. And Cullen, what's my constant term going to be? Move it over to the other side. Absolutely. +2. Absolutely right. So our constant term always needs to be moved over to the other side of the equal sign from our variables, because that's how our calculator has things set up. All right, so now we're down to our third equation. Let's see, who can Adrian, tell me what the coefficient for VA is for our third equation. So -1/15. And then we also take into account the -1/2 from that bit in the front, which you absolutely did. So thank you for that. Let's see here. Addison, what's my coefficient for VB in my third equation? Yeah, so -1/20. And who can I pick on? Sydney, what's my coefficient for VC? So VC is positive in all three of these terms. So I'm only going to have positive numbers. I can see right here that VC is being divided by 20. So I'm going to have a factor of 1/20. Right here, VC is being divided by 15 ohms. So I'm going to have a factor of 1/15. And right here, the quantity Vx is the same as VC minus VA. So I'm also going to have a factor of 1/2 that I need to add in there. So it should be 1/20 plus 1/2 plus 1/15. And my constant term is going to be 0. And then I solve this system of equations. And what I just got was VA is equal to 1,520 over 91 volts, or 16.703 and some change volts. VB is 2,260 over 91 volts, or 24.835. And VC was 1,580 over 91 volts, or 17.363. Anybody else get those results? All right. So now let's talk about what we can do with those results. So for a problem like this, if it were to show up on an exam, I would usually ask you 2 to 3 questions about it, okay? First question would probably be, what would Vx be? So how would we find Vx now that we know all of our nodal voltages? Literally came up with an equation for it right here, right? So whatever VC is minus whatever VA is. So for us, throw Ashton's calculator around. 1580 over 91 minus 1520 over 91 seems like it's going to be 60 over 91 volts. Other questions that I might ask would be, possibly finding a current. So if I wanted to, let's clean some of this stuff up so I can ask questions about it. So if I wanted to know the current flowing through the 5 ohm resistor from left to right, let's say that this was a current IY, how would I find that current now that I know what my nodal voltages are? So the current's flowing from left to right, so it'll be VA minus VB over 5 ohms. So the current's leaving node A and flowing to node B, so it's A minus B over 5 ohms. Okay. what would the power absorbed by my dependent source be? Let's write this one down here. So the power absorbed by my dependent source, okay? So because I have a source, I'm going to need to know both voltage and current, right? So the current's fairly straightforward. It's half of Vx, because that's what we're told, right? So we know that our current is going to be 0.5 times Vc minus Va. Now, since I'm asking you guys to find the absorbed power, should I put the positive polarity terminal on top or bottom? Top. So that the current is flowing into the positive polarity terminal because we're calculating absorbed power. All right. So let's call this voltage V dependent, the voltage drop across our dependent source. How would I express the voltage drop across our dependent source in terms of our nodal voltages? Yeah, so just VC. Boom. Plug in our numbers, call it a day. So once we know what our nodal voltages are, we can figure out any other voltage, any other current, or any power literally in just one step past finding those nodal voltage quantities. That's why this is such a powerful analysis tool. We're using Kirchhoff's current law, really multiple iterations of Kirchhoff's current law, to figure out every voltage in the circuit simultaneously with respect to ground. And then once we have that information, we can use it to figure out anything else we could possibly need. Okay. All right, so I have another example here, but instead of that, let's go look at homework set number 5, problem 3B, the one that I worked in an annoyingly long way using superposition the other way and told you guys nodal makes it much easier. Okay. So if I'm not mistaken, the circuit looks something like this. I am assured I will have to change the direction on, oh, but there was a voltage source in there too, wasn't there? Yeah, so the dependent voltage source is going to mess things up. Well, that'll be okay. We'll use this as an example to figure out how to handle voltage sources. Yep. I'm not mistaken, this was like 5 IY. Is my right current source up or down, Ashton? Are both of them up? Okay. All right, and I'm just going to throw numbers in here because at this point it doesn't matter. So let's call this. Sure. And this was IY? Okay. I think I only bothered to work out the first half using superposition. I don't know that I bothered to finish the second half because I said it was annoying and pissing me off because it was annoying and pissing me off. But anyway. Oh, well, I'll be damned then. Okay. All right. So we're going to approach this problem using nodal analysis. We are going to have to modify our procedure very slightly because we have a voltage source, okay? We'll see why we have to modify our procedure here in just a moment, but let's run through our steps and I'll add some in when we need them. So our first step is still just going to be find or label or whatever I said earlier, our nodes. So we have this one on the top left. This one on the top right. and then this one on bottom. Now, I have some strong thoughts about where we should apply ground or our reference node when there are voltage sources present, but I'll talk to you guys about that after we work this problem. For now, let's just leave it up in the air. So we need to choose our reference node. So somebody tell me which node is going to be our reference. Camden, how about you? The green node, okay. Interesting choice, but perfectly acceptable. Now we're going to have step number 3, assign nodal voltages. So this is going to be node A, and this guy down here will be node B. Our green node is ground, so we are done. All right, so step 4. Express controlling variables in terms of our nodal voltages. So our controlling variable in this case is the current IY. So Camden, I'm going to pick on you because you chose such an interesting place to put our reference node. What would IY look like in terms of our nodal voltages here? So what node is the current flowing from? Flowing from the green node to the blue node, right? Because this is the IY that we're figuring out. So since it's flowing from ground, we're going to have 0 minus the node it's flowing to, VB, divided by the resistor value. So our current IY is negative VB over 39 ohms. Nothing wrong with this, just an interesting place to put ground. All right, we are going to have a different step 5, so I'm going to leave some space for that. And then here's step 6. And let's call it step 6A. And we're going to attempt to write a KCL equation at our non-reference node. And I'm telling you this explicitly, I'm going to wind up erasing that and writing something else there in a minute because things are about to break, okay? So let's start at node A. So I have this current leaving node A, this current leaving node A, and this current leaving node A. So what's the current flowing down through the current source? Yep, negative 3.8 amps. What's the current flowing down through the 23 ohm resistor? VA minus VB over 23, absolutely correct. And what's the current flowing to the right through my voltage source? Anybody care to venture a guess? So let me say I couldn't tell you. There is literally no way to express that current in terms of our nodal voltages. This is why voltage sources make things a little wonky, okay? So what we are going to do is introduce the concept of a supernode here, okay? So a supernode is just a combination of nodes that encloses a voltage source. So I'm going to outline my supernode here in purple. So my supernode in this particular case contains both nodes A and our ground or reference node. Now, we never write a Kirchhoff's current law equation for our ground node, which means we are not going to write a Kirchhoff's current law equation for any supernodes that contain ground either, okay? So I'm going to erase this guy right here where it says write KCL equations at non-reference node. And I'm going to modify that to write KCL equations for all supernodes that do not contain the reference node. Now, for this circuit, there aren't any supernodes that don't contain the reference node, so we're not going to be able to write an equation there, okay? Anywhere we have a voltage source, we will have a supernode. And our supernode is formed just by lumping together those nodes to enclose the voltage source, okay? We'll practice a couple of more of these here in a moment so that it's more obvious about things. So if I can't write a KCL equation for node A, what am I going to do to get an equation? Not really. I mean, kind of, but not really. So the step 5 that I skipped is going to be write voltage relationship equations for each voltage source. So let me explain what I mean by that. We're going to take whatever voltage that we were given. In this case, the voltage drop supplied by our voltage source is 5 IY. So I'm going to have 5 IY is equal to, all right. So what's the nodal voltage associated with the positive polarity terminal of our voltage source, Memphis? What nodal voltage is at the positive polarity terminal of our voltage source? So VA is at the negative polarity terminal, as indicated by the negative sign. Which one's at the positive polarity terminal? Ground. So 0. Okay. Minus the nodal voltage at the negative polarity terminal of our voltage source, which would be VA. So this is our voltage relationship equation, right? So let's count some things up here. We have one equation here, 2 equations here. So now we just need to figure out where our third equation comes from. Well, our third equation is going to be step 6B, let's call it. write KCL equations for all remaining non-reference nodes, which in our case would literally just be node B. So KCL at node B, we're going to be adding these currents together. So this one, this one, this one, and this one. And all of these will be well defined, right? So what's the current flowing up through my 3.8 amp current source? 3.8 amps. What's the current flowing up through my 23 ohm resistor? VB minus VA over 23. What's the current flowing up through my 39 ohm resistor? VB over 39 ohms. And lastly, what's the current flowing up through my current source on the right? 3.2 amps. Set this equal to 0. Here's my third equation for my three unknowns. And now I can solve this system. So let's solve it. So my first variable is going to be VA, my second variable is going to be VB, and my third variable is going to be IY, because I'm going to be lazy and not do substitution here because I don't have to. My calculator can handle 3 equations, so we're just going to run with that. So let's see. So in my first equation, my coefficient for VA is 0. My coefficient for VB is -1 over 39. My coefficient for IY is going to be -1. So I'm moving this IY over here on the same side as all of the other variables. So that's why the sign is changing there. So it's just -1. My constant term will be 0. For my second equation, my coefficient for VA is -1. My coefficient for VB is 0. And my coefficient for IY is -5, where I'm just moving this whole 5 IY over to the other side with the variables again. Okay. And then in my last equation, my constant term is 0. My last equation here, my coefficient for VA is -1 over 23. My coefficient for VB is +1 over 23 plus 1 over 39. My coefficient for IY is 0. And then my constant term will be -3.8 minus 3.2, or -7. Solving this system, I found VA to be -805 over 57 volts, or -14.123. VB was -2093 over 19, or -110.158. And IY was 161 over 57, or 2.825 after rounding amps. All right, so let's take a crack at homework set number 6. So this is the homework specifically designed to test your aptitude with nodal analysis. And I'm not going to do the most awful one, but I'm going to do one of the awful ones. And we're going to use this to practice and continue learning, as it were. So let's look at problem 4. This is the one that I'm thinking of. That one doesn't have any dependent sources. That's fun. That one's annoying, but not as annoying as I want it to be. Here's a nice annoying one. So we are going to apply the mesh analysis, excuse me, the nodal analysis technique to this circuit here. I'm choosing this circuit in particular because I have several voltage sources that I have to deal with. And so we're going to talk now about where our best place to choose our reference node is when we have voltage sources and all of that kind of good stuff. And we're going to wind up having a system larger than we're capable of solving with our calculators, if memory serves me correctly, which will lead me to showing you guys how to solve systems on MathCAD, because you're definitely going to need to do that for your homeworks and such. So I'm going to draw this terrible circuit. So this is homework 6, problem 6, if I'm not mistaken. And we have a 2 ohm resistor in series with a current source, where our current source has a value of 2 amps, or at least mine does. Then I have a dependent voltage source, negative polarity on the left, 2Vx. I have a current source I2 direction up, so that's 8 amps up. I have a 7 ohm resistor here. Three ohm resistor down here. Let's see, 4 ohm resistor across here. Five ohm resistor here. Vx is positive polarity on top across my 5 ohm resistor. Let's see. Short circuit resistor up here. Short circuit voltage source down here. Positive polarity on the left, if my very short-term memory is correct. V1 is negative 13 volts. And then we have a dependent source across the bottom, negative polarity on the left for IY. Which means I need to figure out where the heck IY is. Current flowing down through our 7 ohm resistor. All right, so I would argue that this is a very significant increase in difficulty from the last couple of things that we've worked. But we're still going to be able to apply the exact same step-by-step process and come out with something. We're just going to have something so big that it needs a computer to solve, because I don't know about you guys, but I don't want to solve the determinant of a 5x5 matrix or whatever by hand. It sucks. So let's run through the steps of our process again. Step number 1, identify our nodes. So we've got one node up here. We've got a node right here. A node down here. We've got this node. This node. This node. This node. And we'll do this bright green. Can you all differentiate the different colors? Okay. All right, so we have however many nodes that is. I didn't bother to count, but it's a lot of them. Okay. Our next step is going to be to select where our ground node is. And so now I'll talk to you about how I choose my ground node whenever I have voltage sources. So if I have multiple voltage sources present, I typically choose my ground node at the node that touches the most voltage sources. And the reason why I choose my ground node at the node that touches the most voltage sources is so that I just get to use a bunch of voltage relationship equations and I don't have to write a bunch of KCL equations for those supernodes. So it makes it the equations that I have to write easier and smaller, okay? So which node touches the most voltage sources in this circuit? The purple node. So purple node touches 2. The red node touches 1. The, I don't know, blue greenish node thing at the top middle touches 1. The orange node touches 1. The light green touches 1. Purple touches 2. That's where we're going to put our reference. Right. So here's our reference node. Now, step 3, we are going to assign our nodal voltages. So I'm just going to work my way from the top to the bottom. So let's call this VA, B, C, D, E, F, and G. Seems like 7 to me. Making sure I didn't miss any nodes, because the only one that's left is the purple on the right that's ground. Ashton, see me screwing anything up yet? Okay, good deal. All right, now we are going to go to step 4. Which is to express our controlling variables in terms of nodal voltages. We have 2 controlling variables in this circuit. I think I scrolled way too far. So let's start with the voltage Vx. Who wants to take a stab at telling me how to express the voltage Vx in terms of my nodal voltages? Patrick. VB minus VE, absolutely correct. Thank you for that. Would somebody else like to tell me how to express the current IY in terms of our nodal voltages? Yes, ma'am. VD minus VG over 7. Thank you so much, Leah. Absolutely correct. So I believe those are all of our controlling variables. So we're done with this particular step, unless I'm missing anything. I don't think I am. Okay. So now we're going to go on to step 5, which, because we have voltage sources, is to write voltage relationship equations for each voltage source. So I've got 3 voltage sources. So let's start with the 2Vx voltage source on the top left. So what's my voltage relationship equation for that 2Vx voltage source going to look like? Yeah. So 2Vx is equal to VB minus VA. Absolutely correct. Thank you, Liam, if memory serves me correctly. Okay, now let's look at the negative 13 volt source. Who wants to take a crack at that one? So negative 13 volts is VE minus 0. Absolutely right. So we'll just say negative 13 volts is VE. And lastly, we have this 4IY voltage source. Who wants to take a crack at that one? Sorry, I scrolled too far. Absolutely correct. 4IY will be equal to 0 minus VG or negative VG. Thank you, Austin. Okay. So step number 6, A, that's how I chose to call it this order, is to write KCL equation for each supernode that doesn't contain ground. So let's go up here and figure out which supernodes, if any, satisfy that criterion, right? So anytime we have a voltage source, we are going to have a supernode. So I'm going to have a supernode here between nodes A and B. I'm going to have a supernode here between nodes E and ground. And I'm going to have a supernode here between G and ground. Realistically, I could actually combine supernode E and ground and supernode G and ground into a super duper node, if you want to call it that. But it's not going to remotely matter because it contains ground, so we don't have to write a KCL equation. Okay. So this is our first time writing a KCL equation involving a supernode. So let's figure out how this is going to work. We're going to treat it just like we've done everything else. We're just going to add all of the currents leaving the supernode instead of leaving an individual node. So that would be this current flowing down through the 2 ohm resistor, this current flowing down through the 8 amp source, this current flowing down through the 5 ohm resistor, and this current flowing to the right through the 6 ohm resistor, because those are all of the currents that are leaving nodes A and node B. Now, some of you may be astute enough to observe that technically speaking, we have this current flowing through the voltage source from left to right that's leaving node A. we also have a current that's flowing through the voltage source that's leaving node B. Those currents are canceling each other out, which is why they're not going to show up in our equation. That's the benefit of writing our KCL equations at a supernode, is the currents that we literally cannot express in terms of our nodal voltage cancel each other out so that we don't have to worry about that. Okay. All right, so let's get on with this KCL equation. So KCL at supernode A, B. Let's start with the current flowing down through the 2 ohm resistor. Who wants to help me out with that? VA minus VC over 2 ohms, absolutely correct. Thank you. I think that was Brandon. Yeah. Now we have, sorry, that should be 2, not 3. The current flowing down through the 8 amp current source, negative 8 amps. Now we have the current flowing down through the 5 ohm resistor. Yep, VB minus VE over 5 ohms. Thank you. Ryan, maybe? What's your name again? Daniel. Thank you. VB minus VE over 5 ohms. And then we have the current flowing to the right through that 6 ohm resistor. VB over 6. Set it equal to 0. All righty. So I want to reiterate that we do not need to write a KCL equation for supernode E ground or supernode G ground, because we never write a KCL equation for a supernode containing ground. Okay. We only use the voltage relationship equations because that's literally all we need. Okay. So now we're on step 6B, where we need to write KCL equations for all of our remaining nodes that aren't our reference node. So to me, that looks like nodes C, D, and F. Everything else is taken care of. So let's start with KCL at node C. So that would be this current flowing up plus this current flowing down. So what's the current flowing up through the 2 ohm resistor? All right, what's the current flowing down through the 2 amp source? Negative 2. So VC minus VA over 2 minus negative 2. Sorry, plus negative 2. That was a brain fart on my part. Sorry about that. Now I believe I said we needed to do one at node D. So at node D, that's going to be this current flowing up, this current flowing to the right, and this current down. So let's start with the current flowing up. What's that going to be? 8 amps. What's the current flowing to the right look like? VD minus VE over 4. And then the current flowing down, VD minus VG over 7. All right, so 8. VD minus VE over 4. VD minus VG over 7. If I make a mistake here because I'm trying to remember what all three terms are before I write it down, please correct me. All right, lastly, if that one's correct, I believe we need an equation for KCl at node F. So at node F, that's going to be this current flowing up and this current flowing to the right. So what's the current flowing up? What's the current flowing to the right? VF minus VG over 3. Absolutely. Was it 2 amps? Actually, nor was I apparently. 2 amps. We're on F. And then VF minus VG over 3. Thank you. All right, so I think this is 9 equations for our 9 unknowns. Again, please, for the love of God, do not try to do this by hand. It is a miserable, miserable experience. This is what computers were made for. So if memory serves correctly, and it very well may not here, I believe I put a link on Canvas for you guys to be able to download MathCAD and all of that kind of good stuff. Let me verify that very quickly, and if I need to do it, I can upload it here shortly. All right, so yeah, so MathCAD Prime 8.0 download link and all that kind of stuff is here on the introduction section of Canvas, so you guys all have access to it as students of Louisiana Tech University. Sometimes it can behave a little wonky when you're off campus, so make sure that you're using the VPN in order to open it up. And if you need details on that, send me an email, and then I will ask Miss Ashley to remind me how to do it, because I don't know off the top of my head. So I'm going to open up MathCAD really quickly, and then we are going to set things up. I apologize for how horrifyingly busy my desktop is. Ashton, stop laughing at me. It's real, real bad. This is after I cleaned it up considerably last quarter when I was having like 30 icons stacked on top of each other because it ran out of room. But anyway. All right, so I don't have the time or the patience for that. All right, so we are going to use a solve block in order to solve this system of equations. It's important that you get your license and all that kind of stuff set up through the university. All of that information should be on that link. The reason why I'm mentioning it is it's because if you don't have a license, this is one of the features that's grayed out, meaning that you can't actually use it. And that's pretty much the only thing we're going to be using MathCAD for in this class. So make sure you follow the instructions and all that kind of jazz so that you can get a properly licensed version of MathCAD. Okay, so our solve block is broken up into 3 discrete parts. Up here at the very top, we have our guess values. So if you guys are familiar with any kind of programming or anything like that, which you all should be to some extent, this is effectively where we are declaring our variables, okay? So I'm going to declare all 7 of my nodal voltages as well as my controlling variables Vx and Iy here. And so I'm going to talk you through that really quickly. So I'm going to start with the voltage VA. I am meticulous about this, but you guys can be lazy. So I'm going to do V and then control underscore so that I get a subscript A. And now I'm going to use the shift colon, and this gives me a special type of equal sign. So this is saying, I think this variable has this value. Okay? Since it's a voltage, I'm just going to guess 1 volt. And I'm going to follow suit and do that for the V through the, or was there any? Okay. As many of them as I need, and then also Vx. So the B, I'm guessing to be 1 volt. The C, I'm guessing to be 1 volt. The D, I'm guessing to be 1 volt. The E, 1 volt. The F, 1 volt. The G, 1 volt. The X, 1 volt. And now I'm going to do IY, and I'm going to guess that's 1 amp. So just to be clear, up when we're typing in our guess values, we're using shift colon. There are 3 different equal signs that you're going to see. That's the shift colon equal sign. Okay. So we have declared all 9 of our variables. Now we're going to come down to the constraints section. And this is where we're going to put in the equations that we came up with. Okay. So let's start with our first controlling variable equation, which was Vx was equal to what? VB minus VE. Okay. So I'm going to use control equal sign here. The V minus the E. So this control equal sign, or this bolded equal sign, is effectively saying whatever is on the left-hand side of the equal sign must be equal to whatever is on the right-hand side of the equal sign. So this is the system of equations that our computer is going to solve, and these are constraining what the results are going to be. So then we had our IY equation. Could somebody please remind me what that was? The D minus the G over 7 ohms. All right. So just as a quick thing here, you don't necessarily have to use units, but I think it's particularly important, so I always do when using MathCAD. If you look here where it says symbols, you can see that we have the uppercase Greek letter omega here. I'm never going to actually go to this menu because that's a pain in the ass. Instead, I'm going to use the keyboard shortcut, capital W and then control G. So let me talk you through why that's the way it is. So lowercase w looks like lowercase Greek omega. So uppercase W is going to give you uppercase Greek omega. Control G is literally just telling it, convert it into a Greek character. So uppercase W, control G gives us ohms. Fantastic question. Let me back up there. It's kind of hard to see because let me hit space a couple of times. So if you hit space once, it highlights the last thing you typed. Hit it again, and it's just highlighting backwards. And then I just press the division. 7 ohms. All right. Then I had my voltage relationship equations, if I'm remembering correctly. So what was the first one of those? So 2Vx VB minus VA. Okay. So for this particular equation, that 2 has a factor, or excuse me, has units of volts per volt, so it's a unitless quantity. So nothing bad is going to happen if I just put in 2. But if we have any dependent sources where we have like a current controlled voltage source or something like that, we need to actually put the units of volts per amp in. Otherwise, MathCAD's going to tell us that we have an error because the units are not compatible. So here specifically, because I'm dealing with a voltage controlled voltage source, the units don't matter because volts per volt just cancels out to 1. But if we have current controlled voltage sources or voltage controlled current sources, we do need to put the units in for the scaling coefficient in order for MathCAD to handle all of everything correctly. So just making a point to point that out. And we'll see it here in a moment, I believe. Our next voltage relationship equation was negative 13 volts is equal to VE, if memory serves me correctly. And then our next voltage relationship equation was 4IY is equal to some voltage. So in this case, that 4 has units of volts per amp. So I'm going to put that in explicitly. 4 volts per amp times IY is equal to negative the, okay. All right, and now we are down to our Kirchhoff's current law. One thing that I do want to point out here, so the size of each section will just continue to grow, so it's not going to matter if you overshoot things. You can always just make the solve block bigger and all of that kind of good stuff. All right. So let's do that first KCL at our supernode equation. Somebody start rattling off stuff and do it slowly because I'm a slow typer, please. Yeah, so it was VA minus. All right, and then we had negative 8 amps, if I'm not mistaken. And then we had the B minus something over something. E over 5. So VB minus VE over 5. Okay, what's next, Janae? All right, and I think that one's finished. All right, what's my next equation, please? So VC minus VA over 2 ohms, okay? All right, it equals to 0. Thank you. Apparently I need to make myself a lot even bigger. Thank you, Janae. Next equation, please. All right. So this next thing that I'm going to do here isn't technically required, but in my opinion is very good practice, and I'll show you what happens if we don't do it. Okay? So I'm going to set up a matrix here. Because I have 9 unknown quantities, I want a 9 by 1 matrix. So I'm going to go over to the matrices tab and come down here to where it says 9 by 1. And I'm going to move this down here. And now I'm just going to put in all of my variables. So VA, VB, all the way through VX, and then IY. I need to make sure that I'm using the exact same labeling that I used above. Right. And now I am going to shift equals find open parentheses, and now I'm going to put all those variables again. So VA, then VB, then VC, etc. All right. And now I'm going to use the normal equal sign. And it takes it a minute, it thinks about it, and then gives me all the results. Okay. So let me talk about what the purpose of that matrix is. Effectively, I am storing all of these variables in this matrix so that I can use them outside of my solve block. So for example, if we wanted to determine, let me go back to the circuit diagram here. Let's do something relatively easy. If I wanted to find, here we go. The power absorbed by my 2Vx voltage source. So the power absorbed by my 2Vx voltage source. We know that this would be the voltage drop across that voltage source, which is literally 2Vx times the current that is flowing into the positive polarity terminal. To me, the current that's flowing into the positive polarity terminal could be expressed as VA minus VC over 2 ohms. That's one possible way to express the current that's flowing through that source. We could also express it in terms of VB related things, but that would be a pain in the ass because there are so many currents on that side and there's only one current on the other side. So that's why I'm using this, right? So 2Vx times VA minus VC over 2. So I'm going to put it back in my MathCAD sheet. As soon as I figure out where the hell my cursor went. Not connected. All right, so P of 2Vx is equal to 2 times Vx times VA minus VC over 2 ohms. Now I wound up getting negative 132.727 watts, right? Now, just for illustrative purposes, copying it. So I'm going to delete this matrix. And now it doesn't know what any of those variables are. So unless we store them in that matrix, they can't be used outside of the solve block for any subsequent calculations. So that's the purpose of storing everything in that matrix. So again, it's not explicitly required, but it is very good practice, at least for this class, where we're going to have to do further manipulation of our quantities after we solve for our nodal voltages in order to determine currents and powers and things like that. Okay. So let me just throw that matrix back in there. And again, putting it back in, everything comes out all pretty. All right, we have 15 minutes left for the in-class assignment, so have fun getting started on, I don't know, the first problem.